So in the previous series of lectures, we actually developed the equivalent electrical circuit for a single phase transformer. And to quickly summarize this, we have here a primary voltage and a secondary voltage and a primary current and the secondary current. In between we have an ideal transformer. So everything that's not ideal we've actually removed from this. So we've split the transformer into two parts. The ideal transformer that has no series impedance and infinite shunt impedance, and we've taken those qualities outside of the ideal transformer to represent them as components. So we actually allowed for the resistance of the wires in the primary, the resistance of the wire in the secondary, and we've denoted these as R subscript P and R subscript S. We've allowed for the fact that the flux does not actually, the flux from the primary does not link the whole turns of the secondary, and we've referred that or denoted it as XP. And the same for the secondary, so any leakage flux is represented as X subscript S for secondary. Then we have allowed for the shunt components. So these were the series components. We've also allowed for the shunt components, and the shunt components are made of two components which are connected in parallel. R subscript capital C, which is the core losses. So these would represent the eddy current losses and the hysteresis losses. So they will account for these losses. As I've said previously, there is no such thing as a resistor. It's not actually a physical resistor that we can find or see. It's actually a means of representing these core losses by using a resistor. The other component which actually we've accounted for is the fact that we have what is called a magnetization current, and that magnetization current actually magnetizes the core and actually exists even when there's no load on the secondary. So you would see here, even when there's no load is connected here, and this is open circuit, there's still some magnetizing current flowing in the transformer. And this component, which is an inductor, accounts or represents this magnetizing current, and the magnetizing current was observed to lag the voltage by 90 degrees, and the best component to represent a current lag of 90 degrees with respect to the voltage is an inductor. And so this actually completes the equivalent electrical circuit model for a single phase transformer. What we'd like to do today is to start simplifying this model to make it much more practical to use in real life. And to do this, we actually go to the turns ratio, because the ratio, we want to use this to actually be able to reflect the secondary into the primary. We want to see what does the secondary part look like when we see it from the primary. And to do that, we actually resort to what is called the turns ratio. And the turns ratio is actually the ratio between the terms of the primary to the terms of the secondary, which also is actually the voltage of the primary with respect to the voltage of the secondary. So, for example, if A is 10, this means this is a step down transformer, because when we say step down, we're referring to voltage, not current. So, for example, if A is equal to 10, then this is a step down transformer, which means it is stepping down the voltage. So when we use the term step down, we're talking about voltage. When we use the term step up, we're also talking about the voltage. And the ratio of the number of turns is the same as the ratio of the voltages. So let us assume we wanted to try to represent this transformer with a load. So if this transformer had a load at the secondary, connected to the secondary, and let's assume this was an impedance, and it was an impedance of, let's say, Z, subscript capital L, meaning it's a load, the impedance of a load. And here we have A to 1, which is the turns ratio. And we're asking the question, what would this impedance look like if we actually want to see it from the primary's point of view? And we can prove that actually this circuit can be simplified as follows. So we can actually have A square ZL. And in fact, this circuit will be equivalent to this circuit from the point of view when we see it from the primary. So when looking through this point, we actually see ZL multiplied by A square. Not by A square. And we will use this now, we will use this representation, this simplification, to try to reflect this onto the primary.